One drawback of using integration by parts is that if you need to do it more than once, there get to be a lot of terms that fly around, and it can be tricky to do all the bookkeeping. One method of keeping all the bookkeeping straight that is pretty popular on the internet, you can search on YouTube for it, is called the Tabular Method. Some people call it the DI method. How this works is, so I'm not going to work through a bunch of examples. There are a few ways of handling this DI method or this tabular method, but what I want to show you is why this method works. So suppose we want to integrate, say, this product, f of x times g of x. So to use the DI method or the tabular method, you choose one of these two functions that you're going to differentiate and one of these two that you're going to integrate, which makes sense. You're just choosing which is u and which is dv, right? That's part of doing integration by parts. So to start out with, we're looking for the integral of this product. So let's say that we have decided that f should be the one that we differentiate, and I should be the one that we g should be the one that we integrate. Okay. So at the beginning, what we're going to do is build a table here, but wherever you start the table, the tabular method, you do this sort of diagonal multiplication to get your result. But wherever you stop the table, on the last line of your table, you have to add a term giving you the integral of this product, right? So if we write down the integral of the product of these two, what we get is the integral of f times g. Well, yes, that is the integral that we're looking for, right? So if we choose a function for d and a function for I, and then write out the result given by this table, yes, we do get something equal to what we started with. Of course, these are exactly the same thing, so this hasn't actually told us anything yet. So the way this tabular method works is you can write down as many rows in the table as you want, and for each row you differentiate the thing in the d row. So I'll put the derivative of f. And to write, I'm going to need to keep track of how many times I've differentiated f and how many times I've integrated g. So to do that, I'm going to put a d whenever I differentiate something and an I whenever I integrate something. Okay, so the second row is going to be, we have the derivative of f and the integral of g. And also, on each row, you have a minus sign that appears. So since the first row has a plus, since we haven't changed its sign, the second row is going to have a minus. Okay, so we get this, and the sort of rule for using the tabular method is you do a diagonal product like this, so f times the integral of g, and then you add a term with this sign, so adding a negative, that's subtraction, and then you keep doing these diagonal terms, but when you reach your last row, you have a term that is the integral of the product, right? Just like when we had just the first row, we had a term that was the integral of the product. Well, now that we have another row, we need a term that is the integral of the product of these two. So the integral of the derivative of f times the integral of g. Right? So if we write one more row, we get this. But look, this is just integration by parts, right? If you started with this product and wrote down integration by parts, this is exactly what you would get. So when we do one more row, right, the first row where we picked f and g, when we do one more row, the tabular method just reproduces integration by parts. So that's why one row works. But look, if adding one row works, then adding any number of rows works. So let me show you why. So if we add one more row, then that means we have the derivative of f and the integral of g, and the sign that we get here is a plus. Okay, so let me write out the result of this table using this tabular method. So again, it's these diagonal products. So we have plus f times integral of g, okay, minus this diagonal product. So derivative of f times the integral of g. And then now we're at the last row in our table, so we have another term, so plus, and it's going to be the integral of the product of these two. So derivative of f times the integral of g dx. So this row is what comes out of the table. But why does this have anything, why is this row correct? What does it have to do with integration by parts? Well, let's do integration by parts on this integral. What we get is f times the integral of g minus, so now we're going to do integration by parts on this integral. So we get, let's see, this is going to be playing the role of u, this is going to be playing the role of dv. So we get u times v, so that's the derivative of f times the integral of this piece, so that's the integral of g, minus the integral of, and then derivative of this piece, so that's the derivative of f, times v, which is the integral of this piece. So the integral, I need a little more room, the integral of g dx. But look, these are equal because we just need to distribute this minus sign, right? When we distribute this minus sign, that's going to make this minus a plus, and so we get what we got from the table. So the reason that this works is because these diagonal products, these are just the pieces coming from integration by parts, or the pieces in front of integration by, well, the first term in integration by parts, and then they switch signs because every time you do integration by parts, you get another minus sign. And of course, when you multiply one more minus sign, it switches the sign from plus to plus and so forth. And then this remaining integral at the very end of integration by parts, that's just the integral of the product of your last row, as you can see here. So you can see that if we did one more row, we'd get integration by parts would expand this piece, but that would give you the same as what you get from the next row in the table with derivative of f, integral of g, and a minus sign. So you'd get the exact same thing if you did integration by parts one more time here. So this is really why the tabular method works. You can see that writing out this table and just writing everything out all in one go can make using integration by parts much easier. This table isn't a substitute for understanding how integration by parts works, but it is a nice way to keep track of all of the bookkeeping when you need to do integration by parts multiple times. Oh, incidentally, one more thing about this is if you have an example of integration by parts where f is a polynomial, eventually when you take enough derivatives, you're going to get a 0 here. And the reason why you don't end up with an integral term in your integration by parts is because, well, really you do end up with an integral term. It's just that the product that you get from this last thing, so, you know, who knows how many rows you have here, but the very last is going to be the integral of 0 times some number of integrals of g, but 0 times this is 0, and so this whole part just disappears, right? So if you use this tabular method to calculate an integral where one of these pieces is a polynomial, you actually don't end up with an integral in your result, but that's because the integral that you would have gotten was 0.